Good afternoon, my name is Abanoub Hanna and today I'm here to talk about our graduation project FPGA-based hardware acceleration of NTT with RISC-V ISA customization. So the main problem that we're trying to solve is that current encryption schemes rely on having a math problem that current computers find it difficult, so it takes them many years to solve these kinds of problems. However, with the rise of quantum computers, they tend to break these problems in much faster time. So, for example, for the encryption scheme RSA 2048, which is used in website security, classical computers take millions of years. However, a quantum computer can only break it in 8 hours. So there is an urgent need to use post-quantum cryptography. However, many post-quantum cryptography schemes rely on polynomial arithmetic. So, for example, polynomial multiplication may represent 30% of the execution of some lattice-based cryptography schemes. So we need something to do fast polynomial multiplication, and here comes the role of the number theoretic transform. So it's basically a way to do fast polynomial multiplication with the main benefit that it reduces the runtime complexity from n squared to n log n. Due to the divide and conquer approach, which is also used in the fast Fourier transform. So even the equation is very similar to the Fourier transform, but we do the mod q at the end in order to operate on finite fields. An application for post-quantum cryptography is homomorphic encryption. So it's basically a way to allow computation on encrypted data without decryption. So an example for that in healthcare, if we have a third-party provider with a very strong machine learning algorithm that based on some symptoms or patient history, we can make fairly good assumptions about the diagnosis. However, as a patient or as a hospital, I do not want the third-party provider to have access to my raw data. So we encrypt this data and send it to the third-party provider, and he does the computations on the encrypted data, send the result also encrypted, and finally the patient or the hospital decrypts this data. The main problem with homomorphic encryption that working on encrypted data is very slow, so it's 4 to 6 times slower than on doing computations on raw data. So there is a need for hardware acceleration in this part. Okay, now let's talk about NTT integration. So the selected RISC-V accelerator is the Vortex GPU. It's an open source RISC-V general purpose GPU developed by Georgia Tech. The main reason we use GPUs is the massive level of parallelism. So we have two levels of parallelism. We have multiple threads working on a single core, and also we have multiple cores. So a quick comparison between a CPU and a GPU that are currently in the market, we can see that GPUs have much higher number of cores, however in the expense of a lower clock frequency. Luckily, the NTT is a very parallel algorithm, so it's compatible with GPUs. For example, a 64-point entity could be broken down to smaller 2-point entities working in parallel, but may be done on multiple iterations. Okay, now let's talk about integration types. So we have two types of integration, either loosely coupled or tightly coupled. Loosely coupled, we take our component and maybe treat it as a black box and standalone unit that communicates with the CPU, maybe through a well-defined interface such as an AXI interface. The other type is the tightly coupled, that we take our component and we place it inside the CPU or the GPU, so it shares the internal resources. So in our case, we choose the tightly coupled. So in the execute stage, we added our own crypto array that where we will place our entity unit. The first idea that we might think of is doing entity instruction. However, we face the problem that threads are independent, which means that each thread has its own execution unit and its own register file. So any interconnection or communication between two threads cannot be done through a simple hardwire. There must be another way. The solutions that are currently present, NVIDIA proposed an instruction called shuffle, which allows a register file of a certain thread to communicate and exchange data with another thread. However, the shuffle instruction is not in the Vortex ISA, so we cannot use this solution. The other solution is that after each iteration, we go store in the memory, and in the next iteration, we read from that memory. For the custom instruction that we added, we can see that the basic unit in the entity is the butterfly unit. It's composed of three main operations: modular multiplication, modular addition, modular subtraction, and those are the three custom instructions. We also make the mod q constant. hard-coded in the design since it's usually constant for a certain scheme. Finally, we also added a bit reverse since the output of the entity operation is output in a bit reverse order. Now let's see the entity unit, which is placed inside the crypto array. We can see that it's composed of three main units, which is modular addition, subtraction, modular multiplication, which is done using Barrett reduction, and finally the bit reverse unit. All these units are pipelined and require their input to be stable. So we have to do input capture in the beginning. When we receive a valid signal, we store the input in order the operation to be correct. The block after that is the elastic adapter, which is purely a counter that counts the latency cycles in order to raise a valid signal for the pipeline. Finally, we have a stream arbiter, since we might have a scenario where the three units want to write back, and so we need an arbitration mechanism to select only one unit to write back for a certain cycle. On the right, we can see the kernel, which is the code that runs on the GPU. We chose an algorithm that is presented in a paper, and simply the lines that are responsible for doing the entity operation are replaced by our own custom instruction. Okay, this is a quick demo, but before we play it, we have three scripts to explain. We have entity.py, it's responsible to generate random input points and also generate the expected output. It automatically goes and edit the main.cpp, which is the code that runs on the CPU. It's responsible to send the workload and the data that we should operate on the GPU, and also it receives back the data from the GPU and do the final comparison between the expected output and the data that I received from the GPU. Finally, the kernel.cpp is the code that actually runs on the GPU, which contains our own custom instructions. So let's go ahead and play the demo. First, we run the entity.py. We select the number of points that we want to operate on, and then we can see that the main.cpp, we have the input vector and the expected output generated. And finally, we can go run on the terminal. We can select the number of warps or threads, and we go check the run.log file. Now we go check if the test passed or failed. So the test passed here, and the trace.csv, we see our own custom instructions are present in the instructions in the run.log or no. So we can see here multiply mode, add sum mode, and the bit reverse. Okay, now let's discuss the results. So on the right here, we can see a table comparing the speed up of a single core customized RISC-V GPU and a single core RISC-V CPU. We can see that we reach decent speedups, reaching 5x, and the main reason is the thread level parallelism on a single core. We can see that speedup decreases as we increase the number of points, which in other words, increasing the number of threads in the block or the block dimension. And this paper explains that when we increase block dimensions to be higher than 256, it leads to worse memory access patterns, leading to higher latency, which reduces the overall speedup. So for the future works, we first need to test on higher number of cores. As we have shown in the beginning, GPUs have very high number of cores. If we utilize all this number of cores, we would reach better speedups. Also, if we make the entity unit to have its own memory, it would be possible to have entity instruction, which would also improve the speedup. Finally, let's talk about the FPGA system on chip. We have a host CPU, which is connected to the FPGA through a PCIe bus. The host sends the data and the compiled kernel code to the DDR4 memory in the FPGA, and then resets the GPU. The GPU then starts reading from the DDR4 memory and copies that data to its own memory, and then do the computation on of the entity, and finally write back the final result to the DDR4 memory. Then the host reads from that memory the final result and copies it to its own memory. We can see here the AXI interconnect is just responsible for handling the multiple masters and slaves in the system on chip. We have generated the bit stream for a single core and small number of threads. We can see here the implementation report and the pin planning report. Also, the timing report with positive slacks, and finally, the resource utilization. These are the set of references used in the slides, and thank you for your time.